Hello. In this video I want to think through a proof of compound angles. And actually I should preface what follows by stating or by noting that there are many different ways to prove angle sum and difference identities. For example, there are some purely, or what one might describe as directly geometric proofs and representations. There are which would deal more with geometric first principles, and you're essentially just almost purely working with geometry to prove the angle sum and difference identities. And I may do a video on one of those more directly geometric examples in the future. There's also alternatively and quite differently. I know there's another proof that's uses Euler's formula, which is incredibly cool. It's very elegant, and I haven't looked at it in some time. But I may also dedicate a separate video on that particular method to prove compound angles, just because it is very cool. In this video, though, I'm going to focus on another particular proof, and what we're going to do is we're going to start by proving cos A or alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. And after we prove that this identity is true, we'll be able to prove all of the other angle sum and difference identities. And to do this proof, or this particular proof that I want to think through, uses a little bit of geometry at the start, but I would describe it as a bit more of a terse method, in that whilst we are going to consider geometry, some basic geometry, first principle stuff at the outset, we're also going to use the law of cosines and some other identities, including a cofunction identity and symmetry, to derive the rest of our angle sum and difference identities. And so what is cool about this proof, in fact, is that we're using a number of different trig identities in order to prove angle sum and difference identities. And so in that sense it highlights, I suppose, a little bit more the interconnection of all the different identities one might learn in trigonometry. So what we want to start with is a unit circle here. As you can see, I've started to sketch this. My best attempt at a kind of system. You can picture this as being the first quadrant, if you would like, for contextual purposes. And we want to draw two radii, like so. And this proof, I think, is certainly the most common one in the A-level syllabus. It's at least, that's the syllabus that I'm most familiar with, and I know this proof does appear. And actually, I should also note that there are even different variations of this particular proof, and I might do a second part to this video on one of the variations, because it is kind of cool in comparing the two, but not to confuse matters anymore, and I've probably rambled on a little bit too much about that anyway. So, but if you want to see the variation, check out a following video then, in that case, so I think I will do that. So let's start by labeling some points. You can see I've drawn two radii, length 1. The reason that they're length 1, we can just think of the unit circle definition, or you can think of Pythagorean identity. In either case, it's just first principle stuff here. And let's label some points. We've got the origin, so let's label that O. Let's label this point here, let's label it P. Let's just say this is Q. Let's say that this is N. This is R. Yeah. And to start, I suppose we should define these angles. Let's call this angle beta. Let's call this angle alpha minus beta, because this entire angle, this whole thing right here, we can call alpha. So the entire angle is alpha, hence why this angle here for POQ is alpha minus beta. Right, so the first thing we want to think about is just both of these triangles that we see in front of us. So let's start with QON, triangle QON, which I will highlight in magenta as follows. And so let's think, what is the sine of beta? Sine of beta. Well, the hypotenuse is 1, and maybe perhaps I don't even need to write this, but I will anyway. SOHCAHTOA, right? Okay, so sine opposite over hypotenuse, of course. So let's write this sine of beta. Sine of beta is going to be, well, what's the opposite over the hypotenuse? It's qn over 1, which is just going to equal qn. In other words, qn is sine of beta. So we can mark that in, sine of beta. What about cos beta? Well, that would be this entire length ON. So we can write cos beta equals ON. And again, it's just this cos is adjacent over hypotenuse, therefore it's ON over 1, which just equals ON. So cos of beta, this entire length, and maybe I will just highlight this point like this. ON, this entire length is cos beta. Now, what about this? Let's think about this entire angle right here. Okay, because we've got our alpha minus beta. That's a key indicator that we're starting to work toward this identity, which is very good. And so let's first think about this angle right here, this entire angle alpha, which I'm going to highlight like this, and just draw the triangle that we're concerned with. It's POR for this entire length, or angle alpha. Now, what is sine of alpha? Well, sine of alpha, quite simply, is again opposite over hypotenuse. The hypotenuse is 1, so it's equal to PR, this length here, PR over 1, which equals just simply equals PR. And now what about cos alpha? Well, it's probably quite easy to predict that this is just going to be OR over 1, which is just OR. And we can highlight that point as well, if it's at all necessary. We can write this is cos alpha. And of course PR is sine alpha. Now, what we want to focus on, because we have this angle here, this alpha minus beta angle, and we have in our identity cos alpha minus beta, we want to focus on this angle. How are we going to do that? Well, clearly if we look at it right now, this is not a triangle at all, in fact. But what we can do is just draw a chord here between P and Q. And what we're also going to want to do is, what we can also do is draw horizontal here. And that forms a 90-degree angle like this. But let's look, we want to look at POQ. This is really what we want to look at. So let's just highlight that in green. POQ, like this. Well, it might stand out to you or to someone that we know the angle, alpha minus beta. We know the length of two sides. We don't know PQ. So how could we find PQ? Well, if we know the length of two sides and the angle between them, and we want to know the third side, well, we can use cosine rule. And so, this is suppose one of the key steps is that we can invoke or use cosine, the law of cosines, which we know in general will be is c squared equals a squared plus b squared minus 2ab cos c. And this is just generalized form. We can apply this here where we have pq squared, right? PQ squared equals, well, we're going to have 1 squared plus 1 squared minus 2ab, that's just 1, 1, so 2 times 1 times 1, and then the cos of our angle, which is going to be alpha minus beta. So cos alpha minus beta. And so we can simplify this, so let's just do that. We get pq squared equals, well, this is just 2, right? 1 plus 1 is 2, and this is just going to be negative 2, so we can rewrite this as 2 minus 2 cos alpha minus beta. So we're starting to get somewhere, because we're saying, okay, well, we've got now pq squared, some expression for pq, which is what we need, is equal to all of this, and so one might say, well, let's take the square root of both sides, but that's not going to work out so well if we were to do that, I don't think. And so what we really want to do is we want to try to further define this pq. And one way to do that, I suppose, or one of the key, there are a few different ways to do that actually. We could look at the lengths of this, let's call this point right here t. So we could look at the length of pt and tq, and we could use some, we could just use basic Pythagoras, and we could find the hypotenuse. There are a few different methods and approaches, in fact, and it'd be quite easy because we know the length of PR. So PT is just going to be PR minus, like this length here is PR minus PT, right? Or likewise, which would be sine B. So it would be sine A minus sine B. Likewise, we could find the length of TQ because TQ is going to be the same length as Rn. And we know Rn is just going to be cos B, cos beta minus cos alpha. So we could take that approach. But there's a much easier way, and actually a variation on this proof plays on this more. That if we think of this, just say PQ, the distance D, we just focus on that. Well, we can just use distance formula. And you might think, well, how? We don't know these coordinates or whatever, right? But we do know the coordinates, in fact. The coordinates for P here, just cos A, cos alpha, sine PR is sine alpha, right? What about this point Q? Well, Q is cos beta, right? This entire length, ON, cos beta, and sine beta. And so we could now just essentially use our distance formula and substitute in for PQ squared. So let's keep this expression, what we have here, PQ squared equals 2 minus 2 cos alpha minus beta. Keep that aside for 1 second. And let's focus on using the distance formula here to find further define PQ. And so what we can do is with the distance formula is quite basic, right? We know that it's going to be, where should I write this? I'll just write it, well, we've got quite a lot of a big expansion, so let's write it down here. We'll have PQ squared equals x sub 2, I'll write it this way generally, and then we can just plug it in, just perhaps maybe to make it clear what's going on. X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, right? This is just distance formula, this is very basic, and so we can say, well, PQ squared equals, what's x sub 2, cos A? So let's write this, cos alpha minus cos beta squared plus y2 sine alpha minus sine beta squared. And now all we need to do is you could think of it as the FOIL method or distributive property twice, however one wants to think about this, but we're just going to multiply these out essentially. And so if I just move this over a little bit, get space, because this is going to be quite a lengthy expansion, these two brackets. So what happens when we expand this out? Well, we get cos alpha squared, cos squared alpha, minus 2 cos alpha cos beta, cos alpha cos beta, plus cos squared beta. So that's this first bracket here. What about if we expand this? Well, we're going to get plus sine squared alpha minus 2 sine alpha sine beta. Whoops. Sine alpha sine beta plus sine squared beta. And okay, so now we've expanded this out successfully. Now, where does that leave us? That's the question. Well, it leaves us in a good place because we can see here we have, and I don't know if we should maybe use a color. I don't think that's necessary. You can see you have cos squared alpha and then plus sine squared alpha. Well, those are going to equal 1, right? This is the basic Pythagorean identity. Sine squared beta plus cos squared theta equals 1. Right, so sine squared cos squared alpha, so that's just going to give us 1, so we can write that down here. That's 1. What else can we cancel? Well, we've got a sine squared beta plus a cos squared beta. That's going to give us 1 again. And now we end up with 1 plus 1 minus cos, minus 2. So we have 1 plus 1, right? These cancel. This cancels. So 1 plus 1 minus, then what we're left with is minus 2 cos alpha cos beta minus 2 sine alpha sine beta. And so this is an interesting result, I think. You can say, well, this is 2, so it's 2 minus all of this. And of course, this is PQ squared. We most certainly cannot simplify this anymore. Can we? No, there's absolutely no way that we can do that. Having said that, we know that we have 2 expressions here, and actually we can simplify this more, can't we? We could factor out a 2 right here if we wanted to. We have 2, 2, 2. Let's do that. That might actually help. Help get us where we want to go. I'm not sure. Let's just try it. Let's factor out a 2, and so we're going to therefore have 2, let's just say 2 minus 2. Actually, no, that's not going to help us at all, I don't think. Or will it? We have 2 minus 2 cos alpha cos beta. This becomes positive. That's exactly what we want to do. Yes, so let's factor this out. We're going to factor out a negative 2 here. So in other words, we're going to get 2 minus 2 times cos alpha cos beta plus, right, because it's negative, we pull it out, so it's going to be plus sine alpha sine beta. And now we're getting much closer to where we want to be. We've got our cos alpha cos beta plus sine alpha sine beta, just as we want. Up here, we've got our cos alpha minus beta. And so what we want to do now is compare, I think, the 2 results for PQ squared. And in comparing these 2 results, what we end up with is our direct exact expression, actually, isn't it? Where we get, if PQ squared equals this and PQ squared equals this, well, we can set them equal to each other, we can compare the results. And so we get, let's write it down here, we get, well, let's write this first expression here, 2 minus 2 cos alpha minus beta, set that equal to all of this right here, 2 minus 2 cos alpha cos beta plus sine alpha sine beta. And we should be able to cancel something, I suspect. Let's look. What can we cancel? Well, we can divide both by -2, and actually if we subtract 2 from both sides, these will cancel, right? Because then we'd have 2 minus 2, that's 0, that cancels. Then we're left with -2 cos alpha minus beta, -2 times all of this. So if we divide by -2 right across, those will just equal 1, right? Negative time divided by a negative is a positive, or just +1. So we end up with cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. And we've done it. We've just proven the difference identity cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. Now in the next video I will just continue on with this and prove the other sum and difference identities, and then following that I will also just do a very short couple minutes video on a variation of this proof. It doesn't take very long, and just to compare the two methods.